So, we now begin with lecture 30, in which we will continue talking about the structure of polymers. So, in the last lecture we talked about remaining glass related things. So, mainly we looked at the fused silica and the composition of various glasses, in which elements like sodium, potassium, calcium and boron are added typically to lower the glass transition temperature of the glasses. Glass transition temperature is basically the temperature at which the glass starts to soften before it completely melts. So, there is a slight difference between glass transition and melting temperature. Softening temperature is typically loosely talked of as glass transition temperature. Same is true for plastics as well. And then we started with discussion on polymers. Polymers are another category of non-crystalline solids. We looked at the category of two materials, thermoplastics and thermosets. Thermoplastics are the ones which show a melting kind of behavior. Thermosets are the ones which show a decomposition kind of behavior. Thermoplastics are typically ductile, they can be shaped easily. Thermoplastics on the other hand are not very ductile, they are hard and brittle. And it depends upon the molecular weight of the polymers, how will they behave as a function of temperature when you want to use them. So, if I now first start with long chain polymers, there are three categories of long chain polymers that we typically go ahead with. First is called as plastics. Okay. The plastics typically tend to have they have a random orientation of long chain molecules. So, basically there are long chains of molecules, the polymer chains, which are randomly oriented with respect to each other, and the bonding, as I said, along the chain axis, let us say, it is covalent. So, if you have ethylene molecules, these ethylene molecules will be covalently bonded with respect to each other, and then between the chains we have secondary bonding. Okay. So, this is first form of long chain polymers, which is called as plastics, which are essentially long chain molecules which are randomly which are long chains of polymers, but are randomly oriented with respect to each other. The second category is called as fibers. Fibers are basically aligned chains. Okay. The chains, so in this case, the previous case, the chains would be like this. So, they would be, they are long chains, but they are random with respect to each other. Okay. There can be some cross linking, but they are random with respect to each other. In the fiber case, the chains would be quite aligned like this. Okay. So, these are sort of chained aligned structure. Again, the bonding is similar. So, these are along this is covalent, and between these is secondary, which tends to be typically hydrogen, which is slightly stronger than the van der Waals type of bond. Okay. And it is very strong along the fiber, it is extremely strong. So, it is like a tree. If you look at the structure of tree, right, tree has a fibrous structure in which you have molecules, the chains of tree along the bark axis, they are all aligned in one direction and they do not go crisscrossing. So, as a result, tree is very strong along in that direction. So, you need to cut it, so you can rupture the tree along this very easily, but cutting perpendicular to the axis takes a lot of So a lot of effort. So they are very strong along the axis of fibers. Okay. So wood, for example, is it has a fibrous structure. In this case, it would be plastics, would be polyethylene, for example. Okay. Third category is elastomers. So basically these are long chain molecules with cross linking across the chains. So long chains with cross linking, and the cross links are not secondary bonds, they could be primary bonds. So these cross links could be proper primary bonds. As a result, they have higher strength. The chains have mobility at high temperature, they have translational mobility at of chains at room temperature, which provides them a rubber like behavior. So that is why elastomers are basically, they have a rubbery behavior, they act like a rubber. So these are three categories of long chain polymers. Let us see the example of, to begin with, polyethylene structure. So we start with the polyethylene structure. So polyethylene, of polyethylene is, it is basically, molecule is C2H4, and it can be represented as, you have C okay. So all the 4 bonds are satisfied. When it makes a mer, it becomes CC H H H, and now it is open to react on both the sides. It's open to accepting a neighbor on the each side, and this is called as a monomer or a mer unit of polymer. And when you put many of these together, how do you put them? So you can see the top and bottom are long and short, but they are unintentional. So basically, let me just I think, to avoid the confusion, so that you don't think of it as intentional long and short bonds. They are basically bonds of same length. Okay. So these are all single bonds. So this will make a polymer. So this is called as polyethylene, and the basic unit of this is the one shown here in this box. This is the mer unit or the monomer. So for a polymer, you can define the molecular weight of the polymer can be defined as degree of polymerization multiplied by the molecular weight of monomer. Okay. So, how many? So, basically this is N, this is MW mer, and this is molecular weight of the polymer. Typically the molecular weights range between 10,000 to a million. Okay. So, they can contain from low to high molecular weight, but these molecular weights are significantly higher. The structure looks something like this. If I so you have there is an angle between, so there is an angular relation between the molecules. So, you have let us say this is a carbon atom, this is a carbon atom, and you have a carbon atom here. Okay. The angle between these two is typically, it is not drawn very correctly, it looks like as if it is an oblique angle. It is not an oblique angle. Let me first draw the angle. So, the angle is something like this. Okay. So, now I put the carbon atom. The first carbon atom is here, second one is somewhere here, third one is somewhere here. Now, if I, so this angle is approximately 109.5 degree. Okay. And the way hydrogen atoms are attached to it is like this. So, you have these, so hydrogen atoms are attached in a sort of little this kind of fashion. So, sorry. So, if the first one is like this, the second one would be, it would be like that, something like that, crisscross. Okay. So, this is how you then proceed, and the next one will again go here, and the next one will again go here, and this will be like this, like this. So, these are all hydrogen. Okay. Okay. So, this is sort of a, it will make a, you can say that this will make a polymer chain. If I now connect it, this kind of structure it will make. So, this is the polymer chain, and you can see that this is the mer unit. This is carbon, this is hydrogen. So, if I want to, I will just show you a graphic representation of how it looks like. So, this is the graphic representation of how the chain would look like. So, you have carbon atom somewhere in the center, and then you have these hydrogen atoms at various angles. So, 1, 2, 3, 4 like that. All right. Okay. So, now the alternative view to look at that is, you have this as one atom of carbon, this is another atom of carbon, this is another atom of carbon, and these two carbon atoms have the hydrogen atom, one hydrogen atom sitting on the back, another hydrogen atom sitting on the front. Similarly, on this side, one on the back, one on the front, one on the back, one on the front, one on the back, one on the front, one on the back, one on the front. So, if I just right, this becomes a little bit more clearer. Like this. So, okay, on two sides you have hydrogen atoms. So, this is a planar sort of zigzag arrangement of carbon chain, molecules of carbon chain. Okay. So, these make a structure which looks like orthorhombic structure. I will show you here. So, essentially it looks something like that. You have, they make a structure something like this, and you can make the unit cell, which is this green colored unit cell, which is the orthorhombic unit cell of polymeric chains. So, these are all chains, okay? These are all chains, and they sort of arrange in a fashion so that a crystalline form of polyethylene can make a orthorhombic unit cell. So, they tend to have a highly crystalline form of polyethylene will make a orthorhombic unit cell. Now, looking at these chains, the ability of polymers, now you can see that it makes a chain like structure like this, C, 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 and so on and so forth. You can, one has the ability, these chains are susceptible to modifications of the side groups, which can lead to formation of various polymers. For instance, if you all put, we have seen that if you put hydrogens all across, then you will get polyethylene kind of structure. However, if I replace some of these hydrogens with, so this is polyethylene, polyethylene, which is nothing but C2H4N. Now, if I replace some of these hydrogens with, let us say, in this case alternatively as chlorine, let us say here chlorine, then my basic unit is this. This makes what we call as polyvinyl chloride. So, basically it is C2H3ClN. Now, if I make another change here, so this is PVC, let us say instead of Cl I put, let us say CH3. Then it makes what we call as polypropylene, which is commonly known as PP. This is known as PE. This is known as PVC. PVC pipes are so common, right? So, this is nothing but C2H3 CH3N, basically C3H6, right. So, this is how you can tweak the structure of polymer, and this has profound impact on the type of polymers that we have. So, you can have let us say if you have 4 of these groups, ethylene based, basically if I make a classification between ethylene based long chain polymers, all right. Then I have, so let us say first let us define the name, the acronym, okay, and then let us choose the group R1, R2, R3 and R4. So, here what I mean basically is you have, so this is let us say R1, this is R2, this is R3 and this is R4 in one unit, okay. So, R1, R2, R3, R4 and then let us say applications, okay. So, the first one that we have seen is PE, in which all the groups are hydrogen, and this is used for a variety of applications such as bags, containers and so on and so forth. Polyethylene is a very useful material, right? Bags, containers and so on and so forth, vessels. Second thing that we made was PVC. In this case, 3 hydrogens remain the same, fourth one is chlorine, and PVC is a little harder because chlorine is a bigger molecule, right? So it adds to the strength of the polymer. So it's used for making pipes, for example, tubes. Third one is polypropylene, which is PP. In this case, we saw you have 3 groups as H, and the fourth one becomes CH3. Polypropylene is again a nice material which is used for things like making, dashboards in the car, bumpers. So bumpers in cars, the bumpers are a little harder than polyethylene. Dashboards are also harder materials. Buckets are typically made up of, vessels are made up of wherever you require hardness, more hardness than polyethylene, you make it of propylene, and it does not contain chlorine. Okay. So PP is another form. Then you have PMMA, polymethyl methacrylate. In this case, you have 2 hydrogens, one goes as CH3 and another one is replaced by CH3 COO. This is used for a variety of applications, much more harder. It is used for example, glasses, as a window glass. So windows, okay. It is also used as plexiglass that we use in our lab to make variety of things out of this plexiglass, as we call it a plexiglass. Plexiglass is more like a trade name, right. So this is PMMA, polymethyl methacrylate. Then we have polystyrene. So this is polymethyl methacrylate. This is polystyrene. In polystyrene, you have H, H, H and C6, H5. This is for basically, polystyrene is a very well known packaging material. Okay. And then we have some other examples, 2 more examples, let us say a few more examples. PTFE, polytetrafluoroethylene. Okay. In that case, R1, R2, R3 are all replaced by fluorines, F, 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 F. So R1, R2, R3, R4, F, 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 F. And PTFE is something which is a very well known engineering material. It is used for making bearings, it is used for making sliders, it is used for making various other components and devices. So this is for making bearings, for example, rotating parts, moving parts. And then we have so this is polytetrafluoroethylene, okay. And then we have polyacrylonitrile. Here 3 hydrogens remain, one is replaced by cyanide group, and this is basically a acrylic fiber. Where is it used? For the sweaters that you wear, clothing. So wool is substituted by this fiber, which provides you a cheaper yet durable sweaters. Okay. So these are some examples of polymers that we polyethylene based polymers that we see. So essentially, so a long chain polymer basically would look like you have this long chain going, and then you have another long chain going like this, and along the chain you will have molecules sitting next to each other. So this is basically a long chain polymer. And if you want to see the chain configuration, a linear is like this. So, you have these molecules sitting across like this. If I maybe use different color, these are linear molecules, and so these are linear, okay. And the ones which are cross linked are, so you have these as other polymers, you have these molecules, mer units, and if these are arranged, if these are connected with each other using linkers, so you can have these branches here. So, you can have some molecules linking them. Similarly, you can have this linker. These could be complete linkages, these could be broken linkages. So, for example, if it's broken here, let us say it's incomplete, okay, it could be like this or it could be like that, okay. So, this is basically, this would be branched and this would be cross linked, okay.
Cross linking we also have mer units.
Of course, cross linking also, you can have mer units, you can have some other units. Cross linkers are typically different cross linkers. So, cross linkers, for example, when you do vulcanize sulfur, sulfur replaces the makes the cross linkers. So, cross linker molecules can be different. So, these are cross links. So, I don't necessarily.
We can have the secondary bonding.
Yeah, secondary bond does not really cross link. For cross linking, you need to provide some molecule which links the two chain. Okay. So, this is basically a cross linked structure. This is a branch structure where they do not talk to each other. They are close to each other, but they do not talk to, they are not connected to each other. So, this is branch, this is and then you have networked structure. Networked structure could be something like that, like this, less common, but it is possible. So, you have molecules sitting here, here, here. So, this is a networked structure just like you saw in glass, quartz. Okay. So, this is a network structure. And this basically, as you go from here to here to here to here, you increase the strength and hardness. As the side groups become more and more bulkier and heavier, the strength increases. That is what you see in polymers, linear chain polymers. As you go from hydrogen to chlorine to CH3 group or C6H5 group, typically they lead to increase in the strength and hardness. And if you have more cross linking, it is going to lead to even more branching or cross linking. It is going to make it even more stronger and harder because chains will not be able to move against each other very freely. And if you network it, it is going to be becoming even more rigid. So, this is typically the classification of different types of polymers. So, what we will do in the next class is we will look at some more classifications of the polymers and some examples of elastomers and other kind of materials before we completely close the chapter on structure of materials, moving on to the structure, characterization and defects in materials before we complete the course. Okay. Thank you.